Hello everybody and welcome. It's Hugh here at Loxone and we are here with day 5, I think, of our Foundation Series webinar. We've looked at Loxone and who we are. We've looked at config. We've looked at adding in extensions and peripherals, and we have looked at lighting control. Today, we're going to continue the technical. Every day from now on is going to get a little bit more complex and a little bit more difficult because we're going to stop just having different features as islands and we're going to start bringing them in together to give us what Loxone is really all about, a complete holistic automation system where everything works in tandem with each other. Now, today's subject, I always find when I run physical training courses, is one that people have to get their head around more usually because most of our partners are more electrically or technically focused and not a lot of them are heating engineers. And that is the subject of room climate, of heating, because it does require you to have a certain level of knowledge of heating layouts and physical heating systems, as well as how to configure it in Loxone. I'm going to go over a fairly typical heating layout, and that's what we're going to be configuring today. Now, this webinar is going to be around heating. As a system, we can do far more than just heating. In fact, the main function block that we're going to be using is called the Intelligent Room Controller. And it's called that because it doesn't matter whether we're doing heating, cooling, or ventilation. It can bring all three of those in and make them all work in tandem to give us a perfect living environment. And so none of them are fighting each other, and we're not got the aircon going while the heating's going. Perfect room temperature, perfect living space, most efficient as possible. However, for the webinar, we've only really got time to cover heating. So we're going to look over the function blocks that are involved with heating logic in Loxone. We're going to look at how we set temperatures at parameters and what motion does with room climate control. So let's start with some products to do with heating. Now, as always, we've got the mini server, brains of the system. This one here is an extension, and this is a Modbus extension. For anyone that doesn't know, Modbus is a form of communication, usually over either RS485 or it can be over IP as well, where you can talk to certain industrial components. Now, Modbus is very old, but still very common. You will see it on many mechanical ventilation heat recovery units. You'll see it on many heat pump systems. It is still very common. In fact, I've actually got under this desk here an MVHR unit from Airflow, which is Modbus, and I would use the Modbus extension to speak to it. Other things to do with heating and cooling, valve actuators. These are kind of the main product you would consider when you're considering Loxone and heating control. We do a valve actuator in air and a valve actuator in tree. The air version can be either powered by 2 AA batteries, or there is a connector here for 24-volt DC. The connector is a punch down. So IDC punch down like you would do in a patch panel. We give you the IDC tool in the tree extension. So whenever you get a tree extension or the new mini server, you'll get one of the punch down tools. That's the air version. The air version, quite cool, also has a built-in temperature sensor. So while I would never really recommend taking a temperature reading from the radiator, if in an emergency situation or a less commonly used room, to save yourself a bit of money, you could take the reading from there. This will obviously go on your radiator. So where your TRV would normally go on your radiator, that's where the valve actuator goes. All of our valve actuators come with a VA80 adapter, which is the most common thread types. If you've got a bit of a weird or wacky thread type, we do sell other adapters as well. The valve actuator is also available in tree. The tree version does not have a built-in temperature sensor because it's designed to go on a manifold. And then you can see that there are 4 different terminals on the tree version for power and for tree data. Really cool thing about our valve actuator is you obviously get a status back from it. So it will tell you what the current level of it is. It will tell you if there's any faults on the valve, if there's any mechanical errors. So you get a lot of diagnostics with it as well. And it's also fully proportional. So it's not just open or close, it'll actually open or close to a specific level so we can actually control the flow of water into that zone. Really cool device. The tree version as well, the LED on top will blink to tell you how open or closed the valve is. So it will blink green if the valve's closed, it will blink orange if the valve's half open, and it will blink red if the valve's completely open. So again, some nice visual indication from it. Over here, this is the room comfort sensor. So again, air or tree. And at this point, I'll stop showing my screen so I can show you one in the flesh. So this is the room comfort sensor. As you can see, it sits out proud from the wall, and it's got vents at the side to get the humidity and the temperature in. Air or tree. Both versions measure temperature and humidity. The tree version also measures CO2. So this is a great addition, especially for when you want accurate humidity readings, because although the touch switches, the Pure and the touch has humidity in, because it's an enclosed device, the humidity reading is a little bit delayed. So if you're using humidity for ventilation in a bathroom, I would recommend considering the room comfort sensor because it's a much more rapid humidity reading. And then also, if you're looking at doing MVHR control, I would stick a tree version in a couple of core spaces in the house so that you can monitor the air quality as well. So that is the room comfort sensor. This is the tree version. The air version comes with a little stand, so you can actually stand it on a desk or on a bookshelf or whatever, so it doesn't have to be mounted to the wall. Other products related to it, motion sensor. We see these all the time. Core thing about the motion sensor is it's not there to turn on heating. Heating takes too long. It would not be efficient, especially when you consider that underfloor heating with concrete screed could take a good 3 or 4 hours to actually heat that screed up. If we're turning the heating on every time we walk into the room, we're throwing money down the drain. So what it's actually there to do is to extend your heating period. So if you were in the living room and your heating period would normally end at 9:30 at night, but it's a bank holiday, you're staying up late watching a film, it would see motion and it would keep extending your heating period for you so you don't get cold in that room. We've then got the touch switches, the touch and the touch pure. Again, air or tree, both of them contain temperature and humidity sensors. And then finally, door window contact. We only make an air version of a door window contact. If you want a nice flushed in version that's slimline, go for a standard alarm contact, wire it into a digital input. But the one that we do is the air version. And so again, just to give you a quick overview, there is the touch. There is the touch pure. And again, both of these temperature and humidity sensors built in. And then here is the door and window contact. So as you can see, battery goes in the front there, and then on the side, it comes with a little tiny metal pin that goes against the green bit there, and that's how you detect whether it's closed or open. So those are the products that we have for heating control. Now, in addition to this, you could always, don't feel that you can only do wet heating systems with Loxone. If you've got electric underfloor heating, you've got electric IR panels, electric storage heaters, we can do them as well. Remember, we've always got relays. So you're not in any way limited to a specific type of heating system. Doesn't matter whether it's a heat pump, whether it's a gas boiler, whether it's an oil boiler, whether it's a buffer storage tank with an electric immersion heater, really doesn't matter. We can do all of those as well. We can do solar thermal. You're not at all limited. Whatever the heating system going in, Loxone can control it. And this is the system that we're going to be configuring today. This is a very, very typical S-plan heating layout. We've got down here a boiler. It has to forgive that it says things like energy source and mixing valve. It's because this is an international picture. So this is going to be our boiler, going to be a bog standard gas boiler. We're then going to have a mixing valve. Mixing valve we would typically call a blending valve. So when you buy a manifold set, it usually comes with a pump and a blending valve, and it's normally a manual twisty blending valve. Now you can get electronic blending valves, And what we can do then is we can actually measure the flow temperature, and the room controllers can tell us how much temperature they actually need to heat the room up and maintain that heat. And the mixing valve then actually mixes the return water back into the flow to adjust the flow temperature. And that can massively, massively increase the efficiency of your heating system, because for most heating sources, gas boilers, electric sources, heat pumps, their most inefficient time is when they first start. So if we can actually keep this running for longer and actually just mix some cold water into this 62 degrees outflow to make this down to, let's say, 30 degrees, because that's all it needs, and the boiler's then modulating itself, we will actually save quite a lot of money over the course of a year. On this heating layout as well, we will also have a pump. So a pump that you would typically have at a manifold. And we're also going to include a zone valve as well, because you would usually have a zone valve, one or more zone valves. We're going to do it that the zone valve relay is actually wired to the pump, so we would only need to trigger the zone valve. And then over on the manifold, we've got valve actuators on each loop, and then a loop feeds each room. The function blocks that we're primarily going to use is these three. We actually go to about 5 stages in our room climate control, but the 3 that are the most important are these 3. The room controller, one of those goes in every room of the house, and you put a temperature sensor on one side and the valve actuator on the other. The climate controller controls the source, so that's for turning your boiler on and off. And then the temperature controller is for zone valves and pumps on manifolds. So these are the 3 most important blocks. And of course, you can have more than one of these blocks. So let's say you've got a gas boiler, and then in one room you've also got an IR panel as well. You could have a second climate controller. Let's say you've got an S-plan heating system where you've got a radiator loop and a manifold loop. So you've got 2 zone valves. You could have 2 intelligent temperature controllers, and that way you're only triggering the zone valve and the pump for the rooms that require heat. A really, really important thing, though, that I need to mention about our heating control system, it's a zoned heating system. Zoned means all or nothing. So if you have a house and you decide to only put a valve actuator on 2 of the rooms, it will never work properly. You cannot partially zone a zoned heating system, all or nothing. Okay, and then our room climate, we do it in 4 stages. The first stage is the intelligent room controller. That takes the temperature from, say, a touch switch, and based on your target temperature, will control a valve actuator. In this same stage, we've also got a controller called the room ventilation controller, which is for MVHR and ventilation systems. Stage 2 is the climate controller. This looks at the demands of all of the intelligent room controllers that are linked to it. So all of the rooms that would run off this gas boiler. And based on the overall requirement and the overall demand, determines whether it should turn the boiler on or off. Then the third stage is the intelligent temperature controller. And again, dependent on the demands of the room controllers linked to these specific manifolds or these specific zone valves, it will determine whether that zone valve should open. And then stage 4 is a mixing valve controller. So this will again use the data from the temperature controller, and based on the data from this will determine what position the mixing valve should be in, and therefore what the flow temperature should be to the zones. So the way best to think about it is in a traditional S+ plan heating layout, where you would have maybe one boiler with one zone valve feeding the manifold, which feeds, let's say, the ground floor, and then another zone valve feeding the radiators in the upper floor. You would have a room controller in every room, a single climate controller for the boiler, and you'd have 2 intelligent temperature controllers, one for the manifold zone valve, one for the radiator zone valve. And then if you did want to do an electronic mixing valve, you would have one of these for the manifolds, because you typically wouldn't do a mixing valve on a radiator loop. Cool. And so if we then put all of those function blocks into the places that they would be on this diagram, this is what we end up with. Our climate controller is for the source. Temperature controller and the mixing valve is for this bit here, and then the room controllers are for this bit here. I've bored you enough with slides, let's configure it. So this is our config file that we've been working on throughout the week. So again, just connect into it, and make sure up here it says that you're locally connected or remotely connected, however you're connected. Then what we're going to do is we're going to start with that intelligent that intelligent room controller. So we've already got a room of kitchen. We've got a page of kitchen. Everything I put onto this page will go into the kitchen. So I need to add myself an intelligent room controller. And there we go. Once I've added an intelligent room controller, I could add my temperature sensor to it. So I could find myself my touch switch, expand that touch switch, and there is the temperature input. Drag that out, big green plus appears, drop it on, and it goes to TI. TI is the current room temperature. I could also tie in my door contact, because in the demo case, if I just switch over to it, you'll remember that we have a door contact in here. This door contact is wired into digital input 8. So it's actually a digital input. This is not a tree or an air device. It's wired into digital input 8. So I could expand my digital inputs, find digital input 8. Really importantly, please give it a name. So this would be, for instance, my patio door contact. Also remember to give it a category. It could be a sensor, and give it a room kitchen. I could then drag that out, and I could then connect that to IW. I know that IW is correct because if I hover over it, it tells me it's for window contacts. However, there is one really, really important thing to note with door and window contacts. A motion sensor. When there is no motion, the contact is off. And when there is motion, the contact is on. For a door or window contact, however, when the door is closed, the contact is on, and when the door is open, the contact is off. And so this means that functionally, a door and window contact works in the opposite way round to pretty much every other input we work with in Loxone. For all of our inputs, if we go into simulation to show you, they should start their life as off, and then we turn them on when we want something to happen. Whereas a door contact, we need to work in the opposite way round. On means that it's in the safe state, and off means that it's not safe. And so what we need to do, the technical term for this is we need to invert it. We need to make it work in opposite land. So when it's closed, it will send a 0, and when it's open, it will send a 1. Two ways of doing that. The first way is with a function block. And we have a function block called not. And as you can see, inverts the input value. So we could first of all just use a not block. And we could have that sitting in between the contact and the IW input, and this will then invert it. And again, if I show you that in simulation, you can see that while the contact is open, this output is on, and when the contact is closed, this output is off. So that's the first way of inverting. However, for door contacts, it's not my preferred way. My preferred way is actually with something called a negation. To do a negation, on any input or output, you hover your mouse over it until a little black dot appears. See if I can make this even more prominent. So if you can just see my mouse cursor, a little black circle has appeared on it. And when that black circle appears, do a single left click and it turns red. And that does exactly the same as a not block. So that is also an inversion. Okay, so there's my temperature sensor and my door contact. Remember, I can also put my motion sensor in here as well to extend my heating period. Then I would need a valve actuator. So kitchen is downstairs, so it's going to be on a manifold. So it's going to be a tree valve actuator. So add tree device, valve actuator tree. And what I always do is I put the installation place as manifold, but I put the room as kitchen. So the room is where it's actually controlling. Another cool thing with our tree valve actuators is they blink green in sequence while they're on the manifold. And again, just like extensions, you can say what position they're in and then they will blink in the correct order. Just, again, another little cool thing that we do. Okay, expand that valve actuator, drag it out onto the page, but really importantly, it doesn't go anywhere yet. The reason being is that this intelligent room controller has no linking to any other logic. And we already know that we're going to have a climate controller and a temperature controller. And you can see that it's got no linking because here it's telling us that we need to assign objects to it. So all of these outputs at the moment, while they're all usable, they would be if we are just doing a single room's heating and have no global control level. And so what we need to do is we need to, before we connect this, move on to our next stage, our climate controller. Now, a climate controller doesn't go in the kitchen. It's not related to a single room. It's related to the whole house or the whole building. And so what we need to do is we need to create a new page. This page, I'm going to call whole house heating or heating plants or heating control, whatever your naming terminology you like. And the default room for this page is going to be the whole house. You'll see whole house is a default room. You could rename that room as central or whole building or whatever was relevant to the building that you're doing. I could also, because everything I'm going to put on this page is related to heating, also say that the default category is heating as well. And then I need to put my climate controller. So on this page, I need to dump a climate controller. There we go. And there is a climate controller. On the input side of a climate controller, the one that really is important is TO, outdoor temperature. You don't need it. However, if you have a temperature sensor outside, let's say from our weather station, then the climate controller will also do weather compensation. So it has all of the logic built in to do things like weather compensation. It will, by default, take the TO parameter from something called system variables, which is up here. So we can see here outside temperature. And normally that would come from our weather server or our weather station. Weather service is a paid for service. The weather station is obviously a paid for device. However, if you have any other temperature sensor outside for whatever reason, you could always choose define value by logic and then create your own logic for outside temperature. So as an example, the airflow MVHR unit that I've got right down there has a temperature sensor built into its inflow pipe, which I can read through Modbus. So at my house, I've defined it by logic and I'm reading it from the MVHR unit. But it is quite important because weather compensation allows us for a more efficient heating system. Basically, no matter how well insulated the house is, the greater the difference in temperature between inside and outside, the greater the rate of heat loss will be. Cool. So there is my climate controller. Big thing for me, I'm going to rename this because we can display a climate controller in the app. You can see that there is a tick box in use. So I'm going to rename that as boiler. Then we're going to move on to the parameters of a climate controller because the parameters are quite important. The first parameter is the heating type. And this is heat pump / electric or oil / gas. My recommendation would be anytime you are just using a relay to turn it on or off, select oil / gas, even if it was an IR panel or a heat pump, because that removes a lot of the more complex parameters. Heat pump / electric, you'd really only use if you were chucking away the heat pump's controller and you were controlling it completely through Modbus with Loxone. And in that instance, you get things like minimum temperatures and delays for fans and auxiliary heaters, etc. So oil / gas. We can also set the energy costs. So if we have multiple energy sources in this house, we can say which ones are cheap and which ones are expensive. So I could say that the gas boiler was cheap and an aircon unit was expensive. We can also set the mode. By default, it will be on mode 0, which means completely automatic, and it will switch between heating and cooling as required. Now you can leave that at 0, and as long as you say in your room controllers that it only does heating, it'll only ever be in heating mode. Or if you like, you could set it as 1 or 2 for just heating or just cooling. So if I set it as 1, it'll only ever do heating. And then there's a bunch of other parameters, but the only other one that is really critically important is STR, start threshold. And what that means is that a certain percentage of valve openings from the connected room controllers have to be open before it will turn the source on. The reason for that is if you only had, let's say, one room out of a house with 12 rooms, and that one room was only calling for 25% heat, so it only had the valve open 25%, and it could turn the boiler on, you'd be doing something called short cycling. This boiler would be turning on and off all of the time, and it would potentially degrade its lifespan. You could also cause damage to valves and valve actuators by having too much pressure on the system. Basically, it's a no-no. In a modern heating system, you may have something like a differential bypass or a low loss header, which could remove the pressure element, but it doesn't stop the short cycling. In an old-fashioned heating system where you just had a thermostat on the wall, you would typically see that your hall radiator wouldn't have a TRV on. It would just be an open loop, and that's called a sacrificial loop. But those are all traditional ways of achieving this same thing, of making sure there's a particular level of demand. So number one, that hot water has somewhere to go so it doesn't end back up at the boiler. And number two, the boiler isn't short cycling. So that's what the start threshold is. And because it's worked out as a percentage, don't feel that means that you need 30% of the rooms calling for heat. It's 30% of the valve openings. So if you had 10 rooms and you had, I don't know, my maths isn't great, but if you only had 3 of those rooms calling for a certain percentage of heat, it could meet the demand. Or if you had one room, like we have in this config, that one room only needs to be at 30% open. Cool. Now that that's there, I need to have a relay for triggering the boiler. So this would be a relay that's wired into the boiler to trigger it. So this is going to be my boiler trigger. Again, category and room, please. Very important. And that goes on to QH of the climate controller. Brilliant. Now, before we get onto the room controller and back to there, let's get to stage 3, which is the temperature controller. So the intelligent temperature controller. This function block, as I said, is, think of it, anytime you've got a zone valve, it's for this. And you'll see as you dump it onto the page, it gives you a tick box to tick the rooms that it's linked to. And that's because while the climate controller might do every room, the manifold zone valve would only do the rooms connected to the manifold. So if I had any rooms on here that were on the radiator loop, I wouldn't tick them for this block. And then again, please rename it. So I'm going to rename it as underfloor heating manifold. Then again, parameters. So you'll see there is again the TO input for outside temperature, again, because it does weather compensation. Over on the parameter, we've got controller for heating, cooling, or climate control. Now this is important. If you leave it as heating, it acts completely independently of the climate controller. If you want them to work in tandem, set it for climate control and link it to that climate controller. And now, again, I just need to re-click that room controller, but these two are now invisibly linked through that parameter there. And then all of these other parameters are related to the flow temperatures. So if you are doing the level of mixing valve control, this says what the minimum flow temperature and the maximum flow temperature can be. And then all of these, buffer target temperature, slope, offset, start threshold, and gain, are something that anyone who's done PLCs before will probably recognize as a PID controller. PID controller, take a Google of it. Basically, it tries to smooth out a rate of increase so that you're getting to a target temperature quickly or a target level quickly, and then you're maintaining it with very little cycling. So again, it's about efficiency. Then we need a relay for the zone valve. So relay underfloor heating zone valve, And as I said, we're going to do this heating system like you would typically, where the relay from the zone valve, I believe it's the grey and orange core, would be wired to the manifold pump. So we don't actually need to trigger the pump directly. Cool. Now that we've got that level done, let's move back to that room controller. So if we go back to the kitchen, let's double click on the room controller. And in here, we have the option to add that climate controller. So we can add in that climate controller and you can see we can select whether it's heating, cooling, or both. PWM stands for pulse width modulation. And so what that does is it turns the output from being 0 to 10, which is what we use for our valve actuator, to being a digital output, so 0 or 1, but it turns it on and off really quickly to modulate it. So you can also use traditional mains actuators that you would typically get with other heating systems in Loxone through relays. And what we do is we turn them on and off rapidly to modulate them. Cool. Now I've added that climate controller. You can see there it says that it's linked to 1 out of 1 object. And now I'm going to add the valve actuator. So when I drop it on the big green plus, it goes to an output called H1. And this is why it was important that we added the climate controller first, because H1, C1, and HC1 do not exist until this is linked to the climate controller. And so you can see this now works in tandem with that boiler climate controller. Wonderful. Before we move on to the mixing valve, let's take a quick look at the parameters for the room controller and then save in and show you it on the app. So in the room controller's parameters, we have the option for use sunshine information. We'll come into that with shading because that's primarily used for shading. If we've got multiple sources, we can say whether we work them in a priority list or whether we use them all simultaneously. Again, PWM, already explained it. We've also got our schedule. That is our heating schedule. So our schedule is based off of in use and economy. So any bit that's yellow is economy. So that's your setback. The idea being is that even if you're out at work between the hours of 7 a.m. and 6 p.m., you wouldn't turn your heating off. You would put it back to a setback because that's more efficient. It's always more efficient never to let your house get too cold in days that you would be occupying the house at certain hours, rather than to let it get freezing and then have to crank it all the way up to 20, 21 degrees. The only time you turn your heating truly off is when you go away on holiday. And so that's what this is here, an operating mode for holiday. And then the green is our comfort temperature. Then in the other parameters, we've got the parameter for the comfort temperature. Don't worry, you can set this in the app as well. Tolerance. Tolerance is much easier to understand from a picture of a graph, which I believe I've got on the slideshow. But essentially, if you're doing both heating and cooling, you want to have a dead band in comfort so that it's not bringing both on at the same time. And so it'd have to get 1.5 degrees above our comfort temperature for a period of 30 minutes before it switches from heating to cooling mode. As we don't have any source of cooling, tolerance doesn't really matter. We then have our economy minimum. So that is when we are in economy mode, how many degrees under comfort is the room allowed to get? There is no right or wrong for this. It's dependent on the parameters of the room and the house. So if my comfort was 21, I could say that 16 was my economy. So I would put 5 degrees there for not in use. Max is when we are not, so when we're in economy, how far above comfort could it get before it starts trying to do things like shading and cooling to cool the room down? If I don't have active cooling, I just really need to set that high enough so it's not going to be telling me off. Then got our frost protection. So this is when we do go to off. So when we do go on holiday, and this is an absolute. So don't let the house get below 5 degrees because pipes will freeze. I would personally set that to 10 in a UK house because we do tend to have external pipe work. And then overheat protection is again, when we're on holiday, how hot maximum can the house get? Valve standstill, it's quite cool. Once every 14 days, it will completely move all of your valves up and down to make sure that the valves aren't sticking. because in the summer, you're not going to be using your heating, but once every 14 days, it'll completely drive the valve so that they don't stick when it does come to winter. And then we have some overrun timers. These are related to external logic that you would do to trigger comfort, etc., etc. The important one is TMV. So how long it extends our heating period for when we're still occupying the room at the end of our schedule. 1800 seconds is 30 minutes. And then finally, delay of window contact. So how long a window or door has to be open before it will actually turn the heating off in that room. And it's set to 5 minutes. And that's because if we just quickly opened our patio doors to get something from outside or take the bins out, we don't want our heating to turn off and then straight away turn back on again. So it has to be open for 5 minutes. However, because I want to simulate this for you and show you it working, I'm going to set that down to 5 seconds for the time being. Cool. Then I'm going to save in the mini server and I'm going to open up our interface. So now in here, kitchen, here is our room controller. So you can see we're currently in comfort mode. I want to be at 21 degrees. The room is currently at 22.5. So nothing for the room to do. If I started pressing this plus here, I would start adjusting my desired temperature. So I could crank this up really, really high to force it to bring the heating on for me to show you what would happen. And as you can see, that only overrides for your normal schedule. At the end of my schedule, it'll go back to how it was before. In the app, I can also adjust all of those temperatures in the app. And I can also adjust my schedule in the app. So this isn't something that the customer can't touch. The customer can freely use this and touch this. Don't know if you just heard, but a relay just clicked. Back on config in live view, you'll see that now because there is a heating demand, the boiler is on and my zone valve is open. You'll see on the kitchen page that in a minute, it will also ask the valve actuator to open as well. Under the whole house room, I've also got my boiler. So there is my boiler and it's telling me that it's heating up because heat is needed in the kitchen. Wonderful. So let's quickly end with the mixing valve controller, just if anyone does want to go to that level. By the way, this would be a fully working heating system. There'd be no need to do the mixing valve controller unless you were doing a new build and really wanted to do efficient heating. So for the mixing valve controller, first of all, I would need the function block. Then I would need an actual mixing valve I could control. Loads of brands make them. You can get them relatively cheap through to relatively expensive. You can get them as 2 relays to open and close, a 0 to 10 volt output, 24 volt, 230 volt. You can get loads of different options. I'm going to assume a mains one with 2 relays because they tend to be the most common and the easiest. So we would have 2 relays, one to open the mixer and one to close the mixer. Again, please remember room and category. I'm a really big stickler for room and category. Makes your life easier. Drag them out onto the page. The open relay goes to Q1. The closed relay goes to Q2. And then the mixing valve controller to work, we need to compare 2 things. We need to compare the desired temperature against the real temperature. The desired temperature comes from the intelligent temperature controller, AQF, flow target temperature. And so what I'm going to do is link AQF to T. But I'm not going to draw a line like that because it would get messy. So instead, I'm going to do something called a reference. I'm going to drag to an empty part of the page, let go, take my mouse to T and left click. And that then links them together without that horrible line in between. So flow target temperature to target flow temperature, done. The second thing this needs is the real flow temperature. To do that, you would strap a probe to the pipe or you would have a probe in a thermo well in your hot water or buffer tank. You would quite often do this through 1-wire. So we actually have a 1-wire extension and we do sell 1-wire probes as well. However, to show you this actually working, I'm going to use analog input 1 on my demo case because that's this potentiometer here. This reads 0 to 10 volts, and you can get 0 to 10 volt temperature sensors as well. The important thing you need to do with them is you need to correct them. So you need to say that if you're receiving 0 volts, it would actually mean that it's, let's say, minus 35 degrees. And if you're reading 10 volts, that it actually means that you're reading 90 degrees, or whatever the read range of that temperature sensor is. So this is how you correct it. So 0 volts equals minus 35, 10 volts equals 90. Then drag it out, stick it on AI, rename it, and make sure the category and the room are correct. So this is going to be our flow temperature. Wonderful. Save that in. And when it's saved, again, we will go on to live view. Here we go. So start live view. Oh, whoops, I pressed save in again. Silly me. Wait another few seconds. Okay, start live view. You can see at the moment the boiler is on. The zone valve has not turned on yet. And that may be because my room has reset. Yeah, it has. So crank that back up to 25. Here we go. Zone valve is open. The mixer is currently closing. The mixer is currently closing. We are desiring 40 degrees flow temperature, and we're currently at minus 35. So as I start twisting this potentiometer, you can see there that the temperature is adjusting. So if I go above or just round about our desired temperature, so we're now at 51.9 degrees flow temperature and we want to be at 40. This has a 60-second sample time. So after 60 seconds, this will start adjusting itself as required. But there we have it. We have the room level, the boiler level, the zone valve level, and the mixing valve level. Last thing we could do is just quickly show you a room with a radiator. So let's say the bedroom. So new page for the bedroom. Default room would be the bedroom. We would again have an intelligent room controller. That would again be linked to the climate controller. We would again have a temperature sensor. So something like a touch tree. Installation place would be the door in the bedroom. Oh, not the bathroom, bedroom. So temperature in there. Don't necessarily need motion or door contacts if we don't have them. This would be a valve actuator air because it is a radiator. So valve actuator air on the radiator. And again, that wants to go on there, onto H1. But the big difference here under whole house heating is while both of them are controlled by the climate controller, this is not going to be on the underfloor heating manifold temperature controller because it's on a radiator zone. And so what we would do is we would have another intelligent temperature controller, this time for the radiators. Again, linked to the climate controller. This time only for the bedroom. And then that would be our radiator zone valve. And then that is a complete heating system. The only thing you would do is an intelligent room controller in each room. Somebody's asked, for outside temperature, could we use a touch tree? Yes, please just bear in mind it's IP20. So don't stick it out in the rain. But if you've got, let's say, a decking area with an overhang, I don't see any reason why it couldn't go on the wall outside as long as it's covered by the overhang. And yes, then you could use your outside temperature from the touch switch. The recommendation for outside temperature sensors is always that they're mounted a meter off the building. The reason for that is your building does actually create a microclimate. It will be slightly warmer within the first meter of the perimeter of your building. So with like a weather station, it's always recommended that you put it on a pole a meter off the top of the roof. Cool. Last thing to show you, really last thing to show you on heating schematic and heating layout. Room sizes, I'm going to mention again, critically important. The room size is used in all of these calculations here to do with heating and cooling up periods, because remember that Loxone heating and cooling learns. It learns the heating and cooling curve of each room, and so it knows when to turn your boiler on to get to the room at the right temperature at the right time, and how to maintain the correct temperature to give you an efficient system that you never have to adjust the schedule for. To show you that working in real life, if I show you our office, and let's go to, let's say, the cinema in our office. So this is our cinema, that's our desired temperature, and that's our current temperature. So you can see there just how accurate Loxone can get your room. But room size is really important for that. Brilliant. I think that about covers it for the logic for heating in Loxone. Let's just finish up with the last few slides. So that was our layout that we've done, and we've done a bedroom and a kitchen in this layout. But other than that, we've done everything the same. Climate controller for the boiler, mixing valve controller for the mixing valve that contains the temperature sensor, and an intelligent temperature controller for the zone valve. Different temperatures in different rooms of the house at different times of the day. Schedule in each room, temperature in each room, warm living room, cool bedroom. Perfect, exactly what we want. Motion, as I mentioned, can be used to extend your heating period. So that's why I didn't tie a motion sensor into the bedroom, because I probably don't want to extend it in the bedroom. But in the kitchen, I may want to if I'm sitting down late at night. We could also, if we wanted to, cancel any overrides that have happened through the motion sensor when we leave the room using the R input of the room controller. R is a reset, which cancels any overruns. And on the lighting controller, there is an output RQ, which does a pulse, so a momentary signal, whenever a double click is detected on a switch. So we could take RQ to R, and then that way, whenever we double click in that room, as well as turning off the lights, it would also cancel any overrides we've done on our heating. Those are some of the core parameters. Those are the parameters for a room controller, for a climate controller, and for a temperature controller. Remember, you can always look at all of the documentation, both on our website and using the I symbol on a function block. And hopefully you're starting to see just how powerful Loxone can be. Our heating and cooling system is amazing. I really don't want to just toot my own horn and say how amazing it is. I have had professional heating engineers come to our training courses saying that they have to go to the level of commercial BMS systems to get heating logic as good as ours. And there is a lot more involved with setting those systems up and making them work. If you would like a welcome package like I've been using, as always, please get in touch with Megan. But thank you ever so much for joining. I hope you've enjoyed. Please join me again from Monday. So I do like a weekend. So we will continue this from Monday. From Monday, we are going to be looking at, if I just remind myself, the next subject will be shading. Then we're going to have music, then intercom and access, security, overview, and tools. But thanks everyone for joining. See you again next time. As always, I'll stay on for about 10 minutes for a Q&A. Goodbye.